Hello, my name is David Juncker. I'm a professor in biomedical engineering at McGill University from Montreal. And I would like to thank the organizers of the 5th Digital Congress on Nanobiotechnology and Bioengineering for inviting me and giving a chance to present our work. So my presentation is on high-resolution, low-cost 3D printing and photo inks for microfluidics, organ-on-a-chip devices, and tissue engineering. I know it's quite a mouthful, but I hope you will enjoy this presentation. So if you want to reach me, you can find me here on my address. Let me try to get a pointer here under these coordinates, and it's also my LinkedIn that you can connect to. So let me try to move here with the different cursors. Okay, yeah, but first thing, I'm actually co-organizer of the Microtask conferences in Montreal this fall. It's 13th to 17th of October. So I'd really like to welcome you all to Montreal. It's the wonderful fall season where you have wonderful colors. And Microtask is very diverse. It overlaps with a lot of the methods here. We just had our initial submission deadline, but there's a deadline in July. And so we're really we're looking forward to welcome many Brazilian colleagues and from everywhere around the world to Microtask. And I know there's already a few Brazilians who submitted posters for the initial abstract. So I'll have the acknowledgements first. As I start, I'd like to acknowledge all the fundings we have received, as well as the many collaborations that really have been driving this work. But more importantly, I'd like to thank all the members of the lab. And we have really a great lab and a great atmosphere. And Montreal is a great place to live and to do research. And I think that's kind of the character of our lab. And our lab, also, as I just give a brief introduction here, is quite diverse, both in terms of the personnel and in terms of the topics. It's centered on microfluidics and micro and nanofabrication, but from all these different areas that we expanded, I'll be talking today about a few specific ones, and namely the organ-on-a-chip parts, 3D printed microfluidics, and then in particular on 3D printing and bioprinting, and also a bit on ink design. And if you want to learn more, again, you can find our lab on the web with additional information. So for today, I'll have a presentation with a brief introduction on 3D printing, photo printing, and photo inks. And then we'll talk about lab on a chip and capillary circuits and which is really how we got into 3D printing, because we saw really an opportunity to redefine what is a lab on a chip. Then we'll move to organ-on-a-chip devices. And then as a later part of the talk, we will speak about low-cost, high-performance, and I think they deserve high performance in many ways, LCD printers, and see how we can develop inks for these 3D printers and then also apply them to microfluidics, organ-on-a-chip, and tissue engineering applications. And then I'll conclude this presentation. So let's jump right in. So the motivation for this work in the organ-on-a-chip field in particular is the drug development, which now is very lengthy, costs over $1 billion, 10 to 15 years, and actually often ends up in failure at various stages. And in the course of drug development, we need models to test drugs, and one of them is cell cultures, as you can see, or animal model. The problem, they are not a good model for our human biology and the physiology, and hence they often do not replicate critical aspects. And that's where organ-on-chips can play a role. And where this has been now accelerated as the FDA has recently approved organ-on-chip data as a replacement for animal models, and hence we can now, there's a real role for organ-on-chips to play in the approval of drugs. And so there's really now a big incentive there. And of course, beyond that, there's also a scientific interest in studying human physiology in organ-on-chips, because we can model in ways that we cannot do normally. And so what is an organ-on-a-chip? I think there's many different organs on a chips, and I really have a very superficial review here, but I'd like to highlight a few critical points. So this is from the lab on a chip, a cover, and so in essence, they are microphysiological analogs. They represent an organ or multiple organs of our body, and so that we can study, for example, the drug response or how they communicate. Typically, because they have to be at the scale of cells or spheroids or organoids, are made by microfabrication, which remains kind of a cost and slow process. However, they're often replicated into PDMS. So PDMS is an elastomer I'll have maybe a little bit more information later. That is transparent, as you can see here. So this big transparent part is PDMS. It's oxygen permeable, so cells can live in here and survive, and it's biocompatible, and it can be readily molded, so poured, cured, and then separated and sealed on various surfaces, and then filled with different cells. And here we see an example of a central channel here with 2 side channels, and these are often filled with different tissues and organs that then communicate over these small length scales. And they typically use capillary valves, which is one of the areas that we work on in the microfluidics work. Now, as I said, it's quite labor intensive, and so how could we potentially 3D print these organs on a chip? And here we go into the field of bioprinting. And so let's have a first view on bioprinting. And when we speak about bioprinting, many people think about direct writing as shown in this video here. Let me see if I can start that. Oops, no. Let's go back here, and I have to get out. I have to click here. Okay.
The concept of printing living tissue isn't new. It's called bioprinting, but it can be a slow process.
If you truly want to recapitulate everything about an organ, one might think about the need to write every single cell in its final location. Now, if you did that at a rate of about 1,000 cells per second, it would take over 1,000 years to...
Oh, okay. Now I'm sorry, I cut it. But he was saying it would take 1,000 years to print a heart. And this is why bioprinting faces enormous challenges. And this researcher, Kalar from Stanford, they're working on printing organoids. But so basically they make large structures. But so in short, bioprinting faces a severe trade-off between resolution and speed. And this is where we have taken a different approach, and that's the one of photo printing. And so photopolymerization 3D printing is it's really what started bioprinting, and it's shown in this patent here, where we have a brief schematic of the description, where we have a bath, a projection system that cures the resin at the top of the bath, and then the print sinks into the bath as layers are being polymerized one after the other. Now, this is the initial concept. Today, they're implemented slightly differently, so I just want to briefly go over that. So here, and they're called resins typically here, and here I have to go back to my mouse again. So here, and so a vat is filled, oh, I'm not sure, maybe you hear the sound here. A vat is filled with resin. UV lamp is turned on. This hardens the resin where the lamp is. Then there's a build plate that will go up. Now, new resin flows in here. It doesn't have to go up that high. A new layer here is formed, and these layers can be patterned. It's not shown here. And then finally, it's lifted out of the ink or the resin, separated, and the print is done. So it's a layer by layer process. And this is really the important aspect of this step. Now, one of the techniques for printing is called digital light processing. And so this is a projection-based system like classical projectors in the classrooms. And here we have some of the specifications, so 50 micrometer pixels, Fourier 27s. And here is one of the big points, 2 million pixels or 4 million pixels even. That means that every layer that is being projected, an image, we can have 4 million pixels at once. And one layer takes a few seconds. So we have a very high information. So we can print high resolution and large numbers very quickly. And this is where this has a superior performance to the direct write printing. Now, there are challenges here, and we'll address some of them in this presentation, or discuss some of them in this presentation. Now, initially, ourselves and many others still actually to this day, they 3D print structures and then they replicate them into PDMS. And here I told you PDMS is being molded, so it can be poured, cured in the oven at 60 degrees and separated, and then it makes this transparent rubbery material, and that works wonderful for making these structures. But if you want to 3D print, you need to be careful to be able to separate it and have a spray. So you need to make multiple replicates before it works. And this is widely used. However, this has limitations. Well, it's still kind of a slow process here. And of course, if you have complex structures that cannot be replicated at the surface, then we cannot make, for example, embedded inside channels. And this is where that's directly 3D printing of the final product is, I think, a worthwhile approach and one of the ones that we have been pursuing. And so, no, we don't want this anymore. And now when we speak about photo ink, also known as a resin. It really includes three key components, and one is the monomer. So this is the part that makes the body of the ink, a photoinitiator that will absorb the light, make a reactive, absorb the light, make trigger the reaction or catalyze the reaction of the monomer to form a polymer, which is then the build plate, and then finally a photoabsorber, which is there so that we can tune exactly that the light doesn't penetrate too far into the ink, so that we can make actually thin layers, and we'll come back to that. And then together they make a photo ink. And so there's many commercial ones, and then we can also make custom photo inks out of PEGDA, and I'll come back to that. And this is in particular to achieve biocompatibility and also other properties such as surface wettability. And so when we speak about resolution, we already saw they have pixel size 10 to the 100 micrometer. And so in XY, this is a big determination. And in terms of thickness, then it's the step at which the printer moves, which defines this. So typically that's of the size of the pixel or a bit larger. But then a very critical aspect is that when we move these layers, we have to be very careful for making embedded channel, because if we expose too much light, when we want to make an embedded channel like this one, well, when we make the closing layer here, it might also cure this one. And when we make the next closed layer, still some light might penetrate and then eventually cure all the uncured resin inside of this channel and make a clogged channel. And so in fact, the greatest challenge in 3D printing is to print cavities or microchannels. And of course, that's our interest, microfluidics, and that's also very critical for organ on a chip because we need to print these microfluidic structures. And so a very critical part is to design a photo ink that is suitable for high resolution printing of these embedded structures. And if you take commercial inks, they give you specifications that might be very good, but when you try them in practice, and here we see the size of the channels, you can see that the smallest achievable channel is 500% or even 1,000% larger than the ones they actually specify. So you cannot trust manufacturers on this. And the reason for that is that their light penetrates way too far into the ink. And so when we design an ink, it's very important to consider the light penetration into the ink. And maybe some of you have done adsorption, and one very famous law is the Beer-Lambert's law, which says that light penetrating into media is adsorbed according to an exponential curve. And there's something called the penetration depth or the adsorption height, and that's where the light has 1/E, so about 1/3 of the initial intensity. And this is called, for our purpose here, the characteristic depth of penetration, dP. And so it's about the initial intensity over 2.71, so 1/3 roughly of the initial intensity. And this parameter is then what dictates how deep the light will penetrate and how deep it will cross-link the ink. And so now if you want to understand how light and ink will interact, we need to characterize the emission spectra of our 3D printer together with the adsorption spectra of the photoinitiator and the adsorption spectra of the photoabsorber. And so this is what this curve shows, and this really analysis was pioneered by Nordin from BYU. And so the first here we see the emission spectra of the LED, and we then see the photoinitiators, this dotted line, which kind of overlaps, but not very well. So we kind of have a mismatch here already a little bit. But luckily, what we have is a range of photoabsorbers that go well beyond the this LCD, so that they can actually absorb the light efficiently. And so by tuning and choosing the right photoinitiator, photoabsorber in conjunction with the light source, we can optimize how deep the light will penetrate. And then finally, and this is now a result from our lab, we can then make curves where we change the energy dose and then we measure the cured depths. And we can see that this follows an inverse exponential here. So it's really the inverse relationship because it's a logarithmic one here. And that the parameters that dictates this curve is dP, it's this characteristic depth of penetration. And here we extract the dP and we can see it's 56.5 micrometer. So we have a light penetration of 56 micrometer. And so now when we want to print, we can now use this penetration depth and adjust it to get the right depth. And so if you want to make very shallow channels, let's say 50 or micrometer in depth inside, we need to have the optimal layer thickness and an optimal depth of penetration. And Nordin kind of established a rule of thumb. So the optimal layer thickness should be 0.3 to 1 dp, so about 20 to 50 micrometers. So when we have this step by step, each layer should be 20 or 50 micrometer with the dp we have here. And in practice, the resolution we can achieve is about 2 to 4 pixels size and commensurate with the dp. So if we have, let's say, 30 micrometer pixels, well, maybe the smallest channel we can make is about 100 micrometer or around this size. Now, Nordin, they really push this, and they show here, for example, 20 micrometer channel size in their 2017 paper, and even smaller ones. So this is possible. In our work here, we will be restricted to channel sizes of about 200 micrometer, which is sufficient for many of the applications I will be discussing with you today. So let's move on now to our first application, which is lab on a chip. So you maybe have heard of lab on a chip, and there's many instances of lab on a chip using various controls. So here is a multi-layer soft lithography, a PDMS-based device with valves that are being pneumatically actuated, a centrifugal system, or a droplet system with electrical actuation of droplets. And while we call them lab on a chip, in actuality, actually, they have peripherals and they have a computer. And so, there was kind of an insider joke where we call them lab on a chip, but really it's lab around the chip. So can we move to a real lab on a chip where it's all integrated? So like your cell phone, everything would be in the chip. And capillary microfluidics, which basically work on the principle of capillary force, like shown with this paper here, they are all integrated. And so they're affordable, they're portable and self-powered, they're user-friendly, they're equipment-free, they're cost-effective. And here you have an example of a COVID-19 test. That's mine, actually. But are they a lab on a chip? Do they have like some notion of programmability? And are they also scalable? Can we do something more than just like a simple assay where we flow the sample, it flows in, and then the reaction is done? And so this has been actually the work over the last, for my one of the areas I have been working for the last 20 years. And this is a bit what we'll discuss today. Today's journey, or part of today's journey, will be to make these smarter lab on a chip devices where we will show that we can do some programmability and that we also have scalability. We can expand it and make and follow a computer analogy here. And so our proposal is we then a programmable lab on a chip that has no peripherals, that has no moving parts, that has electricity free, so it's powered by free energy, like the paper that sucks up the water, that's free energy, and that's digitally manufactured, which here in our context means 3D printed. And so the way this works is by capillary force. So capillary force is like a force, like from Star Wars, where the smallest dimension of the capillary gives rise to the greatest force because it's proportional to 1 over the radius. So a small radius, high capillary pressure, high capillary rise against gravity. And we can also calculate the flow rate, which is proportional to the capillary pressure here and the flow rate resistance, and then the viscosity. And so this is similar to the electrical relation where the current I, sorry, it's my French coming out, I is U, the tension, divided by the resistance. And so that's the basic principle of flow inside of these circuits or of these channels here. And a very critical aspect is to control the hydrophilicity. So we want spontaneous filling. So we need to store energy in the surface, and this can be done by plasma oxidation. So here we have a PDMS slab that's hydrophobic. When we make it plasma activated, it becomes high energy. It attracts the water that spreads out here, even very strongly attracted. And so for our application, we actually need to control this attraction so that the contact angle of water, which here is about 90 degrees, becomes spread out to be about 30, so 30 to 50 degrees in this range compared to the flat surface. And then we can actually both fill the channels and also stop them at various capillary stop valves. And that's where we can start to have programmability and control over the flow. And so this notion is what we developed in what we call capillary circuits, where we etch structures into a into a microfabricated structure. Here it's a PDMS replica. So this is an older work here. And actually these structures represent capillary flow functions. And this is an analogy to electrical circuits in a symbolic representation. And this is part of why we call it capillary circuits. And so, this is capillary flow. And one of the reasons to actually make it call it capillary is to create clarity, because capillary has been used historically for capillary electrophoresis, which has nothing to do with capillary flow. And then also in analogy to electronics, where we have electrical forces, but then we have electronic circuits. So here we have capillary phenomena, and then capillarics as a notion of the circuits that we're building here. And then we can also, like in electronics, build complex electronic circuits using a library of capillary elements. And I'd like to show you a little bit of that now in the next few slides. But before we get there, I'll bring you back now to the fabrication aspect. So capillary microfluidics, they started in the 80s, so the lateral flow devices you just saw, but then in the 90s with the rise of microfluidics, which really driven by microfabrication. So we can see how fabrication really changed the way the devices were built and what kind of devices were built. That was the second wave, and I would say the third wave now is the rapid prototyping wave, which I think will be mostly driven by 3D printing, and which is where we are active at this point. And so when we think of additive manufacturing and 3D printing, this is the current process flow that we'll show for the next few slides, where we make a design, 3D print it so we can rapidly iterate our designs. Then we rinse it in IPA, blow it dry, put it in a UV chamber to cure it, activate it with the plasma, so to make the right contact angle. And here we use a microfluidic tape to seal it so that we only print open channels, which makes it a little bit easier, and then have a closed circuit. And when we have circuits like this, we can now pre-program the flow. And here you will see 8 channels, but we see that our programmability actually fails. So here it's worked by retention burst valve. So we have pumping by a paper here. And these constrictions here, the smaller they go, the higher they retain the liquid. And so they should go in this series, but because we have imperfection in 3D printing, this system actually fails. And so that was actually the record, I think, of sequential delivery was about 8 at that time, or maybe 10. And how can we go beyond that? And so what we then introduced is this notion of chain reaction. And so I don't know if this rings a bell. Are you guys, or are you, the audience, aware of chain reaction? Could you name me a chain reaction? And I'm sure some of you could. And this is, of course, the example of a chain reaction with a nuclear chain reaction, which then, through fission of one atom, it releases neutrons, which break another atom. And since one atom releases many neutrons, there's an exponential growth. But in nuclear reactor, we can control it such that it's just steady state and self-propagating. And so the key aspect is that there is an initiation event and then a propagation. And the propagation, where one event occurs because of the preceding event, and so it's this event in turn triggers the next event. So it's an event-based propagation. And then finally, we have termination because the fuel is exhausted. And so, do you know a macroscopic chain reaction? And any of you can think a little bit about it while I try to switch my laser pointer here. And if you know, well, here is an example. Where we have polymers, which all of you know, and where we can have one after the other. We can have branching out, we can have scaling up, and we can actually have some level of programmability here. And so this is then what we try to implement on a microfluidic scale, where we have one reservoir that is filled, and when this reservoir empties, it will trigger the emptying of the next reservoir. And then when this reservoir empties, it will trigger the emptying of this reservoir, and so on. And here we can also do some branching where one reservoir triggers 2 reservoirs, and we can start to think algorithmically where we have one reservoir that here triggers 2 reservoirs that then mix, and when that is done, it repeats and repeats this n times. So this is like a bit of loop. Also here, we need, of course, to replicate these structures in series. And this is now an example of how this chain reaction is implemented, where we have this reservoir and we use capillary flow control. So we have stop valves here and retention valves. And so we can fill these different liquids with air trapped in between. And this is the key aspect. And so when this one, and so let me actually go to the next page where you have a video of this. So here are the reservoirs and the air links, and there's the paper pump. And that's the main channel that connects them all. So first we fill the reservoirs, and here we have the air trapped in between. Then we fill the main channel that connects all these reservoirs now. And here's an air link we don't see, but then once this one starts to empty, it empties the air. And only once this reservoir is empty will the air go to the next one. And once this is empty to the next one, and so forth. So here's this propagation of events so that we ensure that they only empty one after the other. And so here we have now 6 reservoirs that were triggered in this way. So I told you we have programmability, but is this now scalable? And this is what I'd like to show you in this video, where we have now chained 4 chips, each with 75 reservoirs, so in total 300 reservoir, and where we'd like to show now this chain reaction, a microfluidic chain reaction here that propagates from one reservoir to the others. And so this is then the filling, where we fill all the reservoir. We have here a joint filling, and then here we see where one reservoir air link fills and then empties, and as this empties, it propagates to the next. And so we have 2 propagation here, one with the liquid and one with the air. And at the end here, we need to go to the other side. And you see the liquid also goes to the other side. And then we can propagate it. And now here we must to connect both the liquid link as well as the air link, and the liquid ink around this chip and across all of the different chips. And so that's a little bit tricky, but the students worked really hard and they were able to make this so that we could now operate 300 little reservoirs, which even with active microfluidics is actually not trivial. Okay, now can we do something useful for this? And so the application that I would like to show you here is an ELISA. And so an ELISA, for the ones who have done it, it's a sandwich assay. We have to antibody code, block, add sample, add antibody conjugate. It's very lengthy, a lot of material. So that's why people like to do it in 96 well plates and with robots, so that even though it's laborious, at least they get a lot of results. So could we now take this algorithm, this protocol, and encode it onto this chip, encode it into the architecture of the chip to make it automated, so that we could just fill the samples, and then the chip would execute them all automatically. We can walk away, have a coffee, and then come back and read our results. And so that's what we call here the ELISA chip, where we have now a chip that operates without peripheral, with no computer and no electricity, and where all the logic operations are encoded into the microstructure. And this is now the operations where we have preloaded the chip. We fill in now the liquid. Now we click it together, and then you'll see here it's an antigen, a COVID-19 antibody test. So we have the antigen on the surface. Then the sample flows in. If there's antibody against COVID-19 protein, the N protein, it will bind. Then we rinse. Then we flow in a detection antibody, which is biotinylated. And then we flow in here the streptavidin with an enzyme conjugate. And then now here we flow the substrate. And look here, you'll see now that the reaction is happening. It's a mock reaction, of course, but that shows that we can then detect. And like a rapid test I showed in the beginning, we have a control and the test line. And so we can now make this complex circuit. And so do we have now digital manufacturing? And I show you the manufacturing, and well, is this really digital manufacturing? Well, still a lot of processes here, and also from a cost perspective, this is also still quite expensive. So can we simplify this process? And here we expanded our ink with one new element. And so we have the monomer. So it's PEGDA we use here. So polyethylene glycol, which is well-known biocompatible material. The acrylate, so this is the cross-linker that can cross-link. Then we have a photoinitiator, a photoadsorber, and here also a cross-linker that will have a second function, namely to be hydrophilic. And so this cross-linker is shown here. It's acrylic acid. And why we added that, it's because when we add it, it makes our PEGDA more hydrophilic. So not native PEGDA is a little bit hydrophobic, so not hydrophilic enough for the filling. Remember, we need to be between 30 and 50 degrees. But with this cross-linker, it becomes hydrophilic enough, just the right amount. So here are the contact angles. And in addition to that, it has long-term stability. That means we can print the chip, we can store it, and then we can use this a few months later, and it will still flow as we like it. And so now our manufacturing process is much simplified because we can direct print a chip from scratch and then use it within a few minutes or a long time after printing. We had to do a number of adaptations because remember we had a tape initially with a hydrophobic roof. Now we are in a situation where we have a hydrophilic roof. And so if we just have a stop valve here, these are stop valves. When the liquid fills, it should stop. Now it will leak. And so now what we need here is actually position the valve here in the center of the channel, and then it will spontaneously stop inside, despite the chip being much more hydrophilic. And we also made round channels, for example, to avoid bubble trapping. And here now I show an example of a chip with a chain reaction with embedded channels that you can see here, and that operates very nicely within this. It's a much eight sequential elements within this kind of chips, demonstrating the functionality. Okay, now let's shift a little bit gear into bioprinting, because I think a lot of you are here in tissue engineering and maybe organ on a chip. And so I'll show you a new ink, which is a porous PEGDA, PPEGDA, we like to call it, which is both gas permeable and cell permissive, because native PEG is actually not good for cell culture because cells can't adhere to it. That's actually why it's biocompatible or a repellent. And here we now added this porous material into the ink, the porogen, and then we wash it extensively, and we can wash out the porogen so that we have a microporous material, and which surprisingly now allows for cell adhesion, and of course is more porous. And the porogen we use is simple PEG here. So it's PEG without the acrylate group. And so once this is mixed in, it stays there, but then it can be washed out after the manufacturing. And so here are examples of gyrate structures that have been manufactured with this ink here, as well as at the bottom you can see different porosities. And we can see that with 10% it's very transparent, but with 20 and 30% it becomes turbid. So when we use higher porosity, we have to take that into account. These are then some SEM pictures of these different inks. We can see the pore size from the image here as well, the PEG concentration and the surface reference. So the more porous, the more rough it is, as we can see, and the mass loss. So when we have 30% porogen, we lose almost 30% of mass, really suggesting that the porogen is being washed out, as we don't see a significant size reduction. And then finally, I think what was very interesting to us, because there was a notion that this PEG material would be non-permeable to oxygen and also to CO2. Yeah, and PDMS, one of the great qualities is that it is permeable. And so we did an oxygen permeability experiment where we had a tube with a barrier cap, and the barrier cap was made of no barrier. So there was no barrier cap, an impermeable barrier out of aluminium made of PDMS or of the different PEG formulations with and without porogen. And then we put them in vacuum, and then we have this resazurin, which in the presence of oxygen converts to pink color. So it's like also used commonly for food storage. And we could see then that, well, without barrier, it would become pink very quickly. Whereas with PDMS, it would only become partially pink. And with zero PEG, it already became quite pink, but we can see that then by adding more PEG, it became more porous. And with 10% PEG, we actually have a similar porosity to PDMS for oxygen, which suggests that PEG might be a really good alternative for tissue engineering and organ-on-chip printing, because it can preserve this porosity. Now, is PEGDA, or the PPEGDA, the porous PEGDA, also biocompatible? And so we did some experiments here where we have different co-incubation of cells with the printed material. So according to these ISO standards here, so here is incubating the supernatant with the cells, and here it's co-incubating a disc together with the cells in a culture plate. And here we tested it with different cells, so cancer cells, MDMB231, breast cancer cells, IMR fibroblasts, human umbilical vein endothelial cells, and then finally 293, also I think fibroblast cells. And we can see that we have a very good cell viability. But very interestingly, in our work compared to previous publications, even without washing, we can see that our ink is actually very biocompatible and becomes even more so with after a 12-hour wash. And so that's very attractive then for these bioprinting applications. Now, we cannot print the cells inside of the ink at this stage, but we can print the ink and then make an organ-on-chip device for culturing cells on it. We can then also culture the cells directly on the ink. And here we use HUVEC because they're very sensitive. And we can see that actually with 10% porosity, we really get a good adhesion, and 20%, maybe the highest one, of these HUVEC cells, showing that this porous PEGDA is favorable and permissive for cell proliferation. We then also compare different cell lines again. These are lung fibroblasts here, again, the cancer cells and the HUVEC cells. with polystyrene as an example, and 0% PEG concentration is our reference value at 1 for all these different measurements. And then we can see the fold change here when we have 10 or 20 or 30% PEG. And we can see slight different response, but a generally increase in the proliferation with a porous PEG here. So we then took it one step further, where we now printed a little organ on a chip device. And in this case, it's a chip device where we want to position a spheroid in a center, and then have a gyroid where we can seed cells in 3 dimensions, so that we have a full access to the spheroid from 3 dimensions through these capillary stop valves. And this is the final structure with a Lunia Canadian $2 coin. So this is printed in 45 minutes, and we can print many, many of these at once, as they are so small. And here's an example where you can fill liquid either outside, and it will not go into the center ring, or we can fill it liquid in the center ring. Will stay only in the center ring, so that we can seed one type of cell on one side and then seed the other spheroid on the other side, or vice versa. This is an example now where we seeded MDA231 spheroids that were then cultured with these lung fibroblast cells. And after 14 days, we can see the proliferation and the migration of these cells into one another, where we could now study cell-cell interaction. So that was the first example. And then the second example here is where we co-cultured it with Hubeck cells, and where we can see that the cancer and the Hubeck cells, they actually start to penetrate. So the vascular starts to form, and the Hubeck cells start to penetrate into the cancer spheroid and form a vascular network that can now vascularize and provide potential blood flow to this cancer spheroid. So this is very promising, and something we pursue. Okay, I see I'm running a bit short on time, so I'll try to speed up a little bit. But I think this is very exciting work, because now we're moving from what's DLP printer, what I've showed you so far, to LCD printers. And so we have classical 3D printer up to now. We're based on mostly DLP or laser scanning. So these are imaging-based system where they project a very small pixel, and they can use 365 to 405 nanometers, so commonly 385, because that's where most inks are optimized, where you have the best photo initiators and also good photo absorbers. But now we have LCDs, and LCDs, they have one big advantage to start off. They're very cheap, very cost-effective. And they have some disadvantage, namely that they have 405 nanometer, and it's not projection, it's actually collimated light. But while they're still interesting, is beyond their very low cost, they have also a very remarkable increase in number of pixels. And here we have, for this price, we get 4 million pixels, about the highest you can get with DLP. But we can now get LCD printers with 58 million pixels, and with actually very small pixel size. And so despite of these limitations, because also they have quite low light intensity, could we take advantage of the very low cost and the very high pixel numbers, which could allow us to make much larger prints with very high information density? And that's actually seeing this price. That's why we thought this might be a worthwhile endeavor and try to make that. And so the first success was with biodegradable elastomer, where actually, interestingly, LCD showed better performance than DLP. And here we also highlight here the notion that now this become very accessible to all, because now anyone can buy one of these cheap printers and just print them at their ease. And so here it's using POMAC, and so this is polyoctamethylene maleate anhydride citrate, which is biodegradable and has been used for implants. And so we wanted to try whether we could 3D print. Now this was quite challenging because it's a very viscous ink. And so we also added a porogen here, and as you can see, we were then successful in making this elastomeric material that can be printed and manipulated. And this was then also biocompatible, and we here show it with the adhesion of Hubeck cells onto a scaffold that was 3D printed using this material. So first demonstration and first attractive. Now the second demonstration is with of high resolution, low cost LCD printing, and here we're pushing the resolution a bit further, is back with PEGDA inks, which have been working with. And PEGDA inks have a very big advantage. They have very low viscosity, which allows faster printing, because now when we raise and lower, the ink can flow much easier, and it's also mechanically more stable. And to address a bit the low light intensity, we added here an additional cross-linker PEDA, which helped us make better structures without in a fairly short amount of time. And so LCD 3D printed structures are actually fairly smooth, and we'll see a bit more images later. And with PETA, when we have good PETA concentration of 2%, we're actually able to print with good fidelity structures or small features here of the order of 3 or 4 pixels, which is roughly the resolution limit of these printers at this stage. But as I was telling you, the challenge is to print internal microfluidic structure. And when we started with a photoabsorber ITX here, and we can see here when we add this, when we have the energy dosage here, increase it, we can only start to have a cure depth that increases suddenly at 7 millijoule per centimeter square, and then raises very steeply. So that means now if we overexpose a little bit, because not all pixels are the same, we are very high risk of actually closing the next layer, especially if we print with 20 micrometer layer, as here the cure depths will rise very, very quickly. And so here we then increased the ITX concentration so that we can flatten this curve, so that if we overexpose a little bit, we'll only cure partially the top layer. And here is the DP of 56 micrometer that I showed in the beginning. Now, interesting, ITX here also acts as a photo initiator because we can see the activation energy goes lower, which means we also need less printing energy and we can print much faster. So we expose about 1 or 2 seconds for this type of printing. And we also here match then the emission wavelengths of the LCD printer. You see it's 405, but it goes actually much further. The photo initiator here doesn't fully overlap the photoabsorber either, but since they at least overlap, we can prevent deep penetration of the photo of the light, and so exposure of the deep layers. And then we can then basically adjust the penetration depth to 56 micrometer with reducing the critical activation energy. And so we have to match, as I said, photo initiator and photoabsorber spectra. And then here are now some examples of what we're able to print. So we could print channels with 125 micrometer radius, here micro CTs, and we have a good fidelity between the design and the printed size. And now what is maybe a bit more impressive is that we can, or here, sorry, is actually a 3D image now of this micro channel. What was maybe a bit more impressive is that we can print very thin membranes, embedded membranes here down to 20 micrometer thickness. Here again, you have the CT scan. And again, we have a very good fidelity between the nominal membrane width and the measured membrane thickness in these structures, or width and thickness here. So this demonstrates the capability. And then to further illustrate this, I'll have now a micro CT scan of a microvalve, which is an activable microvalve, which is here we have a small structure, so to minimize, so to allow resins to be washed out. Then we have the side channel, so we have a control channel on top and the side channel on the bottom, and we have this 40 micrometer thick membrane that sits on this valve seat. And this can then be actuated, and this is the open membrane with a dark ink. This is the activated membrane that closes the channel, and we have an actuation response showing that we can now have a functional 3D printed microfluidic device. And then here we have now reprinted the ELISA chip, but with the LCD printer. I'll quickly show replaying this video here, and this is for interferon gamma, and we have a very good performance, really comparable to classical ELISA, except here it's actually reduced in time, 45 minutes, and has minimal intervention, as we all simply need to load, and we have also overflow reservoirs that minimize the need for precise pipetting, and which you can find in our publications, in this one and previous publications. Now, to wrap this up, I'll show a final proof of concept for the organ on a chip, which we did within 2 weeks because it was a reviewer request for our latest paper. That is based on 2 reservoirs where we can see 2 spheroids with endothelial cells in the middle and capillary stop valve that are 200 by 200 micrometers squared. And this is then a printed device. Here is actually an example. Oops, this is the printed 3D chip. I think it's very small, but maybe you can see it. Or not really see it. Here's actually, since I'm showing things, here's the 3D printed ELISA chip that I showed you before. I think maybe you can see it here as well. So you see we have an ocean. And so this is now coming back to this organ on a chip device, which is, I don't think the camera will focus on that, has these 2 reservoirs. And then here we could then see the spheroids and culture them over 5 days. Now with the LCD printer, toxicity still needs to be improved, but we could have reconfiguration of the cells and also sprouting. Now, one very exciting application of these 3D printed LCD is that we can print on large areas. And here we then use this to print this little organ on a chip device in a 96 well plate format where we have 192 organ on a chip device with 4 inlets each, so 700 something, 768 inlets. And we can then think about high throughput screening of organ on chip devices. And here is then this print plate, sorry, it was cellophane. Maybe you can see a little bit of the reservoirs here that are printed inside of this system. And beyond that, we can now also even think about mass production using these very low LCD printers, because the same device, we can print it in layers with breakable struts. And in a 1 8-hour run, we could print 3,400 devices. And this is with a printer that costs $600. That's easy to operate. So it would be easy to operate 10 of these printers and print 10 times the throughput of this device. And that so that someone could send a digital file, and within minutes, one could start to print in a fair, high throughput manner and produce these type of organ-on-chip structures. Okay, now I showed you this. You'd like to reproduce what we are doing. You can find our designs on Thingiverse and Printables. This is where we share them. And so you can then try to reprint them. We also have the recipes for our inks in the papers. They're PEGDA. They're fairly simple to make. So if you have a little bit chemistry knowledge, it should not be a problem. Or you can, of course, also buy commercial inks that are available from different vendors. And so to conclude this presentation, I showed you digital manufacturing of first microfluidic capillary circuits. I showed you these 4 different goals that we had. I think we meet them here. And I believe they're versatile and programmable, scalable, and they're open to digital manufacturing, because anyone with a printer like this could now make some of these print circuits we made. And to go a bit further, I also showed then the possibility of using this to make organ-on-chip devices and tissue engineering here, and much was based on the development of these photocurable inks. So our lab was really another ink development lab, and 3 thanks to Bahid, who did his PhD, who went into that, and so that we adopted this design of inks. There's a lot of opportunities in 3D printing in designing new inks and to expand the potential and the range of bioprinting. I think that's really where a lot of the research can be done academically. And there's also the opportunity of simply modifying commercial inks simply by adding photoabsorbers into them to improve their performance. And so finally, to summarize, I think what we can have now is a design, a 3D printer, and then you can download the design and print your own chip, be it a microfluidic chip or a chip for organ on a chip or tissue engineering. Okay, and with that, I'd like to thank you for your attention. It was a pleasure to make this presentation. If you have questions, feel free to reach out to me at my email or via LinkedIn, and I hope I'll be able to appear in person to answer any questions you might have. So thank you very much for your attention.